Hi everyone, I am Miss Ross and I'm going to talk to you today about why the ocean floor is so much newer than the ground that we walk on. So we're going to talk about two kinds of plate boundaries today. Convergent boundaries, where plates converge or they come together, and divergent boundaries, where plates diverge and they move apart. So the oldest seafloor is about 220 million years old. Just to put that into perspective for you guys, that is about 2,500,000 average human lives. That's a long time. But the oldest continental crust is 4 billion years old, with a B. So just to get you guys thinking about how huge these numbers are relative to each other, I'm going to challenge you to take that piece of paper, turn it horizontally, and draw a straight line 10 inches big. That's going to be our 4 billion year timeline. Once you've got that, try to figure out where 220 million is relative to 4 billion. So pause the video, take a moment, do that. This is what it should look like. It is totally fine if you were a bit off, but if your line is 10 inches long, then it would only be about half an inch, just a little over half an inch from the left. So if you hate being wrong and you already did the math, you might know that that makes the oceanic crust 1/18th, just about, the age of the continental crust. So our question today is why? Why is some of our Earth so much older than the rest of it? And what is keeping the ocean floor new? Well, there are two very important pieces to this puzzle, which together make a slow, important cycle. The first piece is called subduction, and it occurs only at convergent plate boundaries. You may associate this boundary with collisions on mountain ranges, but this is something very different. And to show you, my friend and I are going to use couch cushions as our tectonic plates. You're dense. As you saw when our plates collided, one sunk underneath the other. That's subduction. When two plates meet at a convergent plate boundary, often one will come out on top and the other will sink back into the lithosphere. The place where that happens is called a subduction zone, or if we're talking about two oceanic plates, it forms a trench. So here's what we're going to do to help you remember. Your hands, they're now tectonic plates. So let's make them collide for subduction. Do that with me so that I don't get too much of a Dora the Explorer vibe, okay, please? What's it called when two plates collide and one sinks underneath? Subduction. And one more time, which process happens at a convergent plate boundary? Subduction. I hope some of you are doing that with me to help you remember, but if you just remember chuckling at me from your bed, I'm fine with that as long as you remember subduction. Anyway, what do you think happens when two huge hard rocks scrape together like that? I'll give you a hint. Go like this. I know that you know that rubbing our hands together creates friction, and that's why our hands warm up. Well, with subduction, that is happening at a much larger scale, which means significantly more heat is being produced. Not only that, but when an oceanic plate goes further into the lithosphere, it's getting deeper and closer to Earth's core, so it's moving to a hotter place. Now, I watched Mr. Atkins tell all your silent foreheads about intrusive igneous rock formation, so I know you know that rocks can melt underground with enough heat and pressure. So what do you think happens to that subducted crust material when it sinks? Exactly. It enters the asthenosphere, which is the viscous molten rock underneath the lithosphere. And voila, seafloor is recycled. There's one more aspect of this I want to talk about, but first, I want you guys to think about what would happen if a continental plate and an oceanic plate collided. Pause this video and write down what you think. The answer is that 100% of the time, it's the oceanic plate that is getting subducted. I know at this point, if we were in person, you would ask, why, Miss Ross? Why always the oceanic plate? Well, the answer is really simple. So I'm going to use a very simple demo to show you. Here we have a bowl of water, super simple balance scale, and two sponges. One of them is wet. Like the oceanic crust, its contact with water allows it to absorb some of the moisture, making it more dense. So, as you can imagine, the denser one sinks. Now we know where some of the older ocean crust goes. Let's talk about where the new seafloor comes from. Well, we just mentioned the asthenosphere. So in this demo, I'm going to be the asthenosphere, and my two very reluctant friends will be the existing oceanic crust. Ready? I know that was quick, so let's break it down. I, the asthenosphere, was under so much pressure that I just had to force my way up between two oceanic plates, and my presence there forced the older, denser crust apart. When this happens in the ocean, the newly forming crust cools and hardens to make the newest piece of the ever-changing seafloor. The place where it happens is called an oceanic ridge. And of course, anytime two plates are pushed apart, we know that we're talking about a divergent plate boundary. What's crazy is that up until the Second World War, we thought the bottom of the ocean looked like a field, basically flat. Henry Hess, a geology professor turned military man, used the equipment intended to find German U-boats to detect the depth of the water every time his attack transport ship was out in the Pacific Ocean. He found that it was far from flat. In fact, he discovered a whole mountain range down there. After the war, he continued his work and discovered that there were several major ocean rifts, and that the farther you move from them, the older the crust gets. His theory of seafloor spreading solved the mystery of why the oldest fossils in the ocean were 180 million years old max, while fossils on the continents could be much, much older. So let's review. We've got new seafloor forming around ridges, which are underwater mountain ranges, as the asthenosphere is forced up through the lithosphere, creating new, less dense crust and pushing the older plates apart. But eventually, those plates meet somewhere at a convergent plate boundary. The denser plate is subducted, and the rock is forced back into the asthenosphere, where it melts and the process can begin anew. Continental plates cannot sink beneath oceanic plates because they aren't dense enough. Land masses will always come out on top, and that, my friends, is why the land we walk on is so much older than the seafloor. Before I let you go, I'm going to give you a couple questions to pause and answer, so I'll read them slowly as you write them down. Number 1, where is the least dense seafloor found? Number 2, why are these processes sometimes called a recycling system? Number 3, what do we call the place where subduction occurs? I gave you 2 terms for this, so bonus points if you remember both. And number 4, what do we call the place where seafloor spread begins? Okay, go ahead and pause. So I will go over the answers quickly. Number 1, the least dense seafloor is found at the mid-ocean ridges because that is where the newest rock is formed. Number 2, we call this cycle the seafloor recycling system because subduction pushes the oldest, densest rock into the asthenosphere, and it is from the asthenosphere that new seafloor emerges. So we are reusing that same material. Number 3, subduction occurs at subduction zones. That one's pretty easy. But if we're talking about 2 oceanic plates colliding as opposed to 1 oceanic and 1 continental plate, then the subduction zone is called a trench. And number 4, seafloor spread begins at a mid-ocean ridge where the asthenosphere oozes up through the lithosphere to Earth's surface. So thank you so much for watching my lesson, you guys. I really hope that you enjoyed it, at least a little bit, and that you will remember about the seafloor recycling system.